Hello, my name is Peter, and I am currently a PhD student at Stanford University. I'm excited to be presenting our latest work on wireless power transfer for automotive applications. Electric vehicles are becoming increasingly popular due to the belief that they are more environmentally friendly than current gasoline-powered vehicles. Unfortunately, a large number of electric vehicles will cause large stresses on the power grid when everyone comes home after work and plugs in. If the charging can be distributed throughout the day, such as when people are driving, the power grid will handle the load much more easily. Up to date, wireless power transfer systems for vehicles have been heavy and expensive, mostly due to the ferrites and Litz wire needed for good coil performance at low frequencies. In this project, we increased the switching frequency from 85 kHz to 6.78 MHz, which will allow us to have a less expensive, lightweight air core design. For this experimental system, we are targeting an output power of 1 kilowatt. The system must be robust to a variable gap with an average separation of 30 centimeters. For ease of testing, all subsystems will be interfaced with BNC connectors, and the system will deliver power to a 50 ohm load. An overall schematic of the system is given below, and we will discuss the design and performance of each of the individual subsystems. The first block is the inverter, shown on the right, which transforms a 400-volt input into a 6.78 MHz square wave. The switches used are gallium nitride FETs from GaN Systems. They have a 50 milliohm on resistance, and we can directly solder heat sinks to the top of them. They are located on the backside of the board. The inverter drives a parallel resonant LC tank, and the inductor is expected to dissipate between 20 and 40 watts. This is very difficult to extract from a wire-wound inductor. Therefore, we use a toroid implemented on a printed circuit board. Because it is planar, we can simply sandwich it between two large heatsinks to solve our thermal issues. This inverter can deliver 1.05 kilowatts to a 50 ohm load with an efficiency of 95%. About 11 watts is lost per transistor, 34 watts lost in the inductor, and a negligible amount of power consumed for the supporting circuits. The board stabilizes at 75 degrees Celsius under continuous operation. Now we move on to the design of the wireless link. The coils themselves are very lightweight and constructed of pure copper tubes that have outer diameters of 12.7 millimeters. These are bent into loops that are 58 centimeters in diameter using a pipe bender. Each loop should have an inductance of 1.43 microhenries and a very high quality factor of 2000. For this geometry, a 30 centimeter separation corresponds to a coupling coefficient of 0.1. In order to use these coils in our power system, we must construct a matching network so that this inverter is presented with the correct impedance. This process is shown to the right. First, we need a good model for the behavior of the coupled inductors, shown in A. Next, we realize that these inductor parasitics can be combined with capacitors to form a series of L matching networks, as shown in B and C. Finally, we can choose the impedance values specific to our system and choose the correct components. These are illustrated in D and E. We measure the wireless link and matching network with a network analyzer and find that the efficiency is much lower than expected. There could be several reasons for this discrepancy. The FR4 board used to construct the matching network is somewhat lossy. Also, the oxidation on the coils resistance. So far, we have ruled out radiation from the coils and metallic objects in the vicinity as sources of loss. We are still unsure of the exact cause of all the losses, so we would appreciate if you had any input. Now we move on to the rectifier. The rectifier is a full bridge rectifier that uses silicon carbide Schottky diodes. The rectifier is expected to have an efficiency of 98%, with 5 watts dissipated per diode. The output filter is a 3-pole constant current filter. It is very compact, allows for a fast transient response, and suppresses the switching ripple. Finally, we connect all of the systems together, say a small prayer, and turn on the power. The system can deliver 1 kilowatt of power at 80% efficiency at a separation of 34 centimeters. Changing the coil separation changes the amount of power delivered, but does not significantly affect the efficiency. In this demonstration, we have shown that it is possible to construct a lightweight, robust, high-power, long-distance wireless power transfer system. This is a step in making automotive wireless charging more practical and accessible for everyone.